Hello again, it's me again. I'm Justin from Microsoft. I work on ONNX ecosystem as well as the PyTorch exploiter. And today, I am going to talk about working with large models in ONNX IR. And could you show the slides, please? Great. So the agenda for today, we will talk about when we're working with large models in ONNX, what are some challenges? This is by no means an exhaustive list, but we'll look at a few challenges that developers usually face and how we can use ONNX IR to help addressing those challenges. We will, for those who have not heard about the ONNX IR project or are unfamiliar with the concepts, don't get worried. We'll go through some of the concepts as a refresher so that we all know how things are represented with ONNX IR. And this talk will have a lot of demos and examples. So there will be a lot of code to look at for those who are interested. Now, the models now that we interact with nowadays and work with nowadays are huge. They often come with larger weights, which means when we are trying to process those models, we need beefy machines and potentially larger memories with the billions of parameters translates to gigabytes or even sometimes hundreds of gigabytes of size of tensors. So what if we don't need all those resources to process those models? And the architecture are oftentimes more complex, which simply means there are more things to keep track of. And with more complicated components like attention and rotary embedding, depending on how you are getting the models, if you are getting them from frameworks like PyTorch, sometimes they don't appear as a single unit as the representation. They come in much more primitive operators and are appearing as much complex patterns. So for optimizations, that just means more complicated patterns to match. Now, before showing everything, just a quick announcement. The ONNX IR now is part of the ONNX organization, so it's now an official package under the ONNX GitHub repository. It's published under the name IR-Py to mean that it is a IR intermediate representation designed for Python. You can get it via pip install ONNX IR right now. And there are sometimes confusions caused by just the naming of the package. People may wonder, now ONNX IR defines the IR itself. Now what is this ONNX IR package? Now the mental model for this that I have, and I think that's quite useful, is that ONNX defines the IR conceptually, as well as a formal specification for how you would serialize the model in disk. Now the ONNX IR project in this talk is the representation in Python. We have native Python data structure and APIs to represent the models that are closely related to the model the protobuf definitions that you will see in the next slide. And it presents itself as an alternative to the protobuf representation and APIs when you're working with the models in Python. Now, this talk is going to be demo heavy, but first I want to describe a few concepts so you don't have to worry if you're not familiar with the project itself. We closely mirror the data structure for the protobuf definition for ONNX. So you will see model proto and graph proto that holds the, that is the main container for the model architecture, and the graph representation translates directly into the IR representations. So on the right is a bunch of classes that we have in the IR. We have the model, node, everything that should look familiar. The two things that stand out, and that is a deliberate design decision, is that whereas in the ONNX protobuf representation, we use strings to represent values. Those are inputs and output to the nodes, and outputs to the graph, etc. We have this dedicated class that's called the value class to represent those information. That just means that it's much easier for you now to traverse the graph and find relevant information for those values. Think you don't now know, there's now no need to have a lookup table, for example, to query what the shape and data types are for the values and ensure that you are looking at the right level for the right information, because there could be nested graphs. You would simply call value.datatype or value.shape to get the relevant information. The second thing that stands out is how we represent tensor in ONNX IR. Whereas in protobuf, we have the tensor proto that stores the tensor as this byte representation. We created the tensor protocol that anyone can implement. And with this interface, we're able to achieve a zero copy and experience and provide this unified interface. So it doesn't really matter where the tensor is coming from. It can come from PyTorch or any framework of choice. As long as you implement the protocol, it is now able to be used as a tensor or a constant value inside the IR, and all the tools downstream that leverages the IR will be able to work with it and understand it. Now, this is a view of what the tensor protocol looks like. It really is a very simple protocol. We ask developers to implement the array interface from NumPy and the DLPack interface that is able to achieve zero copy if the backing data structure implements DLPack. It also has just a simple essential metadata like shape, data type, and metadata props that you will find in a tensor. With that, everything that runs the IR or process the IR elements, entities, will simply assume this protocol without knowing anything on how the tensors are backed. You will see in a few slides how we kind of unify external data representation in ONNX and kind of in-memory representation in ONNX with this same interface, as well as supporting data that comes from PyTorch, etc. Now, this is a diagram that describes the rest of the concepts inside a graph. So you see how everything is represented. More importantly, that I want to point out, if you look at the blue and red blocks, those are how the values and nodes are connected. For each value and node, you will be able to see the inputs and outputs to the node. You will also find methods that are consumers and producers that allows you to kind of traverse the graph without doing anything, without doing any hard work. For the nodes, you will have predecessor and successors, so you can either kind of go from node to node or go from node to value, etc. So that's how all the graph is represented. So it provides intuitive access, and it also provides a simplified data model so that you don't need to, for example, understand how the protos are laid out for dynamic shapes. They are often stored in different fields, etc. That's just a unified API for it. Now, going back to the challenges we just talked about, the first one would be larger weights and how we handle those tensors when we're modifying or working with those models. When we're working with weights in protobuf, there is a 2 GB serialization size limit. ONNX has the way to represent to work with external data. So normally how we do it is by storing things as external data. But that doesn't quite help when we load the model and have C++ interfaces that works on the protobuf data structure, because if we go from the PyTorch to the C++ boundary, we would need to do serialization, and that hits the size limit. And when we're kind of using the protobuf as the data structure for representing the model, all the tensor protos, when we're using ONNX helper, when we're kind of assigning things to the fields and say, this value is equal to tensor proto, that actually incurs a copy. So now everything is now in memory, and not only that, every time you assign things to the main model, assuming you're building it up, there incurs a copy. So there's kind of I/O costs as well. And like I just mentioned, if you have external data and kind of tensor proto as raw data, those are different APIs and different fields. So you need to understand how the external data is stored and be able to parse the offsets, etc., to be able to kind of process the data depending on where they're coming from. With ONNX IR, we don't have the 2 GB limit because everything now is in Python. There's no serialization. And we can share tensors from frameworks, just like I mentioned, from PyTorch, etc. There is an example on the IR documentation where we interoperate PyTorch tensors with JAX tensors and ONNX runtime tensors, and those can be used together. With external data, we also took a step to memory map external data files. So when you load a model into ONNX IR, there's actually no disk read except for creating memory map objects. If you don't touch those data or you don't need to do computation on those data, they're ready for you as that API, but there's actually no reading that's going on. And you will see how that's going to be helpful when we process a model that doesn't fit into physical memory. And yeah, they have a shared interface, so it's very easy to work with. Now, as an example, with building the model, we have the ONNX Runtime GenAI Model Builder. By updating it to use the IR graph and ONNX IR as the representation for the graph, and combined with the lazy tensor class, which implements the tensor protocol, but as well delay some computation or transform on the tensor, we're able to achieve on this particular model that's Gemma 3 12B from 190.5 gigabytes, 35 something gigabyte memory usage. And note that the 35 gigabyte is the initial memory that's used when loading the model into the transformers. So we are essentially not using additional memory for constructing the ONNX graph and doing essential transformation on the tensors. The other benefit is that we reduce the model build time from 14 minutes to 2 minutes, and that is only 13% of the original time that's take. So there is a decrease in memory usage, there's a decrease in time, and we also, what's not mentioned here is that we also don't need to cache data to disk. Everything now happens in memory. So that's what has caused the improvement in time. So now is a demo. I'll demo how we use, how you'll be able to use safe tensors now as an external data format in ONNX. So if you could switch to the demo. Thank you. So as you probably know, safe tensors is a tensor format published by Hugging Face, a very popular format if you're working with any Hugging Face model. Now, the way these tensors, or the format lays out the tensors, is that they have this contiguous block for the tensor and a header. So there is a way to kind of use it natively as a ONNX external tensor. now you may ask, how can we do it efficiently then if we have this format for storing the tensor and we want to replace it? In the old days, you might want to kind of read all those tensors in, create tensor protos for them, and then kind of put it inside the ONNX model proto before saving it. Now we could just use IR to do it. To start, I have this example model that is a very simple model, consists of an add that takes in a simple initializer. So right here, we see it's a tensor proto as an initializer. And assuming that it's a large tensor to be replaced. Here, for demonstration, I just make it as 1, 2, 3. But the idea is the same. Now, I created something that's called ONNX Safe Tensors, and on the back of on the back end, it leverages ONNX IR to represent the tensor data to represent the ONNX graph as well as do the kind of tensor replacement. But here, I will just show you the API to see that we're now able to load the safe tensor weights as external data. Not sure, some hiccups for the technology, but we're good. So here, the library is able to read the safe tensors file, parse its header, and directly just replace the initializer with an external data that has the correct offset and length. You could also save kind of existing external tensor to safe tensors, existing ONNX tensor proto to safe tensors, and that can be that is demonstrated in the documentation, and we'll skip it for today. You'll not be able to just load the model natively as any ONNX model with external data to any backend like ONNX runtime, and you'll be able to run inference on it. And this just shows that this is what we expect. 1, 2, 3 plus 4, 5, 6 gives us the array of 5, 7, and 9. So that concludes the first demo. And all of this is possible because we use the ONNX IR as the representation to make replacing initializers very easy and without consuming any memory. Now, the second challenge that we've been talking about is the architecture. They're quite complex. And the example that we want to show is just the PyTorch exporter. With starting from PyTorch 2.5, we use the ONNX IR as the representation for ONNX models when we're building up, when we're translating from the FX graph to ONNX. What that allows us is the ability to have rich metadata like we show in the previous presentation, because now we have a full control over the model that we're building. Previously, we were kind of leveraging the PyTorch graph representation, and it does not give us the access to latest ONNX standard and ONNX capabilities that is possible with ONNX IR. The recurring theme is that we do zero copy of tensors. So if you can see on this line that is highlighted, we just implemented this class that's called torch tensor for the interface, and we give it a PyTorch tensor, and that's it. That's the constant initializer we put in the graph, and every downstream tool that uses ONNX IR for graph transformation, and you will see we have an optimizer and rewriter in ONNX script, will be able to leverage this tensor. And it allows us to run passes on the ONNX model without having to deal with FX complexity or torch graph complexities when the optimizations are unique to ONNX. And the third challenge is now more complex patterns to match. For that, I will just show a quick demo to see how we use ONNX IR to build the rewriter in ONNX script and how we build the function capabilities for ONNX runtime so that we can go directly from a PyTorch exported model to something that ONNX runtime is considered optimal. And if you could go to the demos, please. Thank you. Now, this demo is very short, and I want to demonstrate the APIs that's available. First, we import ONNX IR as usual. While it loads, I will adjust the zoom level a little bit so it's more clear. And we offer a bunch of fusion specific to ORT in the ONNX script rewriter. Normal thing, we load the model. This is very fast because we are not loading any tensors. And we just call optimize for ORT to run all the fusion that's available in the ONNX runtime package. Finally, we save the model, and you can visualize what it is. So let me just go ahead and run it. The model that we're optimizing is the small LM model. It has 2 layers, so it's not very big for demonstration. But it should show you what the fusion rules is able to achieve here. I set debug equals to true, so you will see all the outputs that this tool is giving you. It will show, what patterns were matched and how they were replaced, etc. And I will now just visualize the model so that you can have a direct comparison of what it looks like. The tool I'm using is Model Explorer, and we're able to create an adapter for it. It doesn't have native ONNX support, but we were able to create an adapter for it also using ONNX IR so that it makes it very easy to translate from the ONNX representation to something that the Model Explorer expects. Here, what I'm going to do is to show you the blocks that were fused together. Let me load rules. So here, in different colors, you will see the different components of the model that were fused. On the color in green is the attention part of the model. You will see on the left is a bunch of primitive operators that's coming from PyTorch. And the rules we have in the ONNX script rewriter is able to recognize it and fuse it into a Microsoft multi-head attention operator. Similarly, we also have this RMS norm that is fused into the simplified layer normalization. And in orange, we have the rotor embedding that is fused also into a single operator for ONNX runtime. That's the Microsoft rotary embedding. So that kind of demonstrate the possibility of implementing rules for a specific target. So you can imagine right now we have more operator support for coming in newer ONNX offset. We'll be able to port those rules to support standard ONNX ops as well. And if you have a custom target that wants a different set of operators, it'd be very easy for you to implement it with the rewriter and kind of leverage those rules for your own use. So here for this demo, I just show the APIs. And we'll go back to the slides, and after this, I will show the final demo, which kind of puts everything together. So you will get a feel of how we can use the rewriter and what it feels like. Now, before that, as a bonus, we also have the passes infrastructure available in ONNX IR. It's something that's inspired from the PyTorch FX pass infrastructure. We have implemented all the common passes like deco elimination, common subexpression elimination, constant folding, and we have something that is a stable topological sort. So normally when you have a topological sorted graph, it doesn't give you kind of stability guarantees and it's not deterministic. We paid attention and care so that the topological sort is stable. If things don't need to be sorted, they will stay in place. These are available to you as part of the ONNX IR library. So you will have access to the passes that we carefully constructed and make sure that they're correct for general use. Now, finally, it's the third demo. What we're going to do is I'm going to show you how you can build a model from scratch with the tape module with some simple APIs. We're going to go ahead and replace some initializers so you'll be able to see the inner workings of the ONNX Safe Tensors package that I just demonstrated and see how you can do the same thing. We'll be building a pass using the ONNX IR to modify the model. The example that we're going to show is a simple model with an attention operator with QKV weights going into the operator. We'll show you how you can kind of merge the operators together if your custom operator wants a certain representation for those weights. We'll show you how you can use the rewriter to do the same thing, so it makes it much easier. So let's go ahead and see the demo. For this demo, what I want to do is I want to build a simple model just like this. It starts with an input with 3 matmos that's doing matmos on the weights. It then is now fed into the attention operator in ONNX and then output. So a very simple case. In IR, we have a tape module for you to easily build a model. It's essentially kind of a recorder for operations that you see and the initializers that you create so that you don't need to, for example, keep track of all the new nodes that you've created and kind of insert them into the graph, etc. To start, we create the initializers and the IR tensor. These tensors are, what the tensors that implements the tensor protocols that I just shared. We have the simple constructor that is able to work with the normal NumPy arrays or anything that implements the array interface and PyTorch tensors. So here you will simply just create a NumPy array and make it into an IR tensor, give it a name, and that's it. Those are the initializers that we just created. To create a graph input, we initialize a value. We specify the type and shape for it, and that's an object that we're going to work with. Now we compute a query key and value by creating the matmul operators. We provide the inputs to the matmul, so that's nothing special or new. And the tape is now able to kind of keep track and remember all the nodes that we just created. These are going to be values, so they can be used as inputs to the next operator, which is attention. You give it the attributes and create an operator attention. And finally, you specify, because we want to make sure that it's a valid ONNX model, it has the data type and shapes that's specified. So we specify them here. Now, combining all of these, we specify the inputs and outputs to the graph, all the nodes exposed via the tape object, as well as the initializers here. And that's the model that we create. So let me just run this, and let me stop the visualizer. And I'll be able to run it and create a model. Now, the second step let me just print it so you can see it. So very simple. It's exactly what we expected in a text form. So you'll be able to see exactly what you've created. Now, the second step is to replace some initializers. Very simply, you can access the initializers from the graph like a Python dictionary. You give the name to it, and you will get an IR value, which has this field const value. All the initializers will have the const value to be not none, and everything that is a const value will implement the IR tensor protocol. We have a display method that's implemented on it, so you get a direct visualization of what that tensor looks like. Now, to replace this tensor, you will simply assign the field with a new tensor. So here I initialize the weight to be all 0, and I will simply assign it and show what it looks like. And you can see that now it is indeed the new tensor that we have replaced. Now, thirdly, we want to build a path to modify the model. Now that we have this model, we want to see what kind of transformation can be done on it. What do we want to do? We want to, again, combine the weights. We have 3 weights. We just want to concatenate them into a single tensor. That's very simple. How can we do that? Here is a pure IR method without all the functionalities with rewriter, etc. So it's using all the APIs that's available in ONNX IR. Now, the plan is this. We have this attention model. Let me put it side by side so we can all see it. The plan is this. We have this model. We'll just identify where the attention operator is. We know for a fact that the inputs will be 3 MetMul nodes, and from there we'll be able to find the initializers. So that's the plan. I created a for loop here to loop through all the nodes in the graph, and you may note that this is implemented so that it can be treated as a sequence of nodes that is iterable. So we implemented everything to have a Pythonic feel to it, so it's very intuitive. We check the op type of the node, and if it's not attention, then we just pass. If it's attention, we do some things to it. We first find the weights, and we're making some assumptions to kind of the input ordering of the weights. These are all inputs to the QKV. We find a producer, which is the MetMul node here. So the MetMul node is the producer of the value that's going into the attention operator. And we find the input. And this should be the weights that we want to concatenate. And with simple assertion, we can assert that are indeed initializers that we're looking for. Now, to build a new initializer, what I'm doing is I'm calling now numpy concatenate on these const values. Now, I'm taking a shortcut here. Usually, what you want to do is you will call numpy on the const value to get a numpy array. But because these tensor protocols also implement the array interface for numpy, we're able to call numpy operators directly on the tensors. And we create an IR value here. Now, from there, we create this new node to do the matrix multiplication with the input value and combined weights. And to make the model valid, we call a split. We do the MetMul first and then split them into the 3 inputs for the attention operator. We add the node into the graph by prepending it before the attention operator. And finally, we only need to do replace all use with to reroute kind of the input to the attention operator so that it now uses the new value that we've just created. We register the initializers to the graph, and we should be done. So with this process, we can now see what the result of this combined weight combined model looks like. You will be able to see the new QKV weight that's combined, which is created, and the new nodes that is created here. Now, there are still some unused nodes and initializers, and that's where the passes come in. We have common passes for you to remove kind of unused nodes. So you'll be able to see that all the map mod that's not used is now removed. And you will also, you'll be also able to run shape inference. And this version of the shape inference we modify such that you will not hit the 2 GB limit. So you will see now the shapes are now filled in for these nodes. And there were previously just question marks. Now finally, we use a rewriter to do the same thing. I think I'm short on time, so I'll go quickly to just show you the pattern and the rewrites that we create. Remember how we were just looking for that attention operator and trying to make sure that we're matching this, the correct node that we want to find. Here, all you have to do is to define the pattern that you expect. I expect 3 map modes going into attention, and so I write the pattern like so. And the rewrite pattern that I want to do is that I want to do the same thing to combine the weights into a single initializer, and I create the map mode and split for the new graph and the attention as well to replace what we just matched here. After defining this, we call the rule API to create a rewrite rule. We'll simply just call apply to model to run the rule against the model. And you will see that it produced exactly the same thing as the manual pass that we just created. And there you have it. You can save it. I have demonstrated the Model Explorer, so I won't do it again. But that's what you would expect. The rewritten model and with all the passes ran through it, and that's what the rewriter is giving you. Cool. Now the final slide, please. If you could switch to the slide. Thank you. And that's all the talk, all of my talk. To get started, please do pip install ONNX IR and get a feel of it. We cannot wait to see what you are going to build with it. Thank you.